Two sample tests of hypothesis, part 2. This is the series of the 3 t-tests. All right, the 3 t-tests. The first type of t-test is the pooled t-test. You're testing two samples coming from different populations where the population standard deviation are unknown. So we're using the sample standard deviation, but we make an assumption that they are in fact equal. The second type of test is the test of unequal variances. So this is where we have population standard deviations are unknown, but they are also unequal. And the last type, right, this is called the paired t-test. This is when we test dependent samples. Okay, so comparing population mean with equal but unknown population standard deviations, again, this is called the pooled t-test. You will not have to distinguish between when the population standard deviations are equal or unequal for this course. However, there is a procedure using something called the F statistic where you actually check statistically to see whether the standard deviations are equal or unequal. So let's read the assumptions of the pooled test. So in this case, the t-distribution is used. And if you have one or more samples that have less than 30 observations, the required assumptions are both populations must follow a normal distribution, which is an assumption you don't necessarily have to make. That's what was assumed when we look at the problems. The populations must have equal standard deviations, and the samples are from independent populations. The method does not require that we know the standard deviation of the population. This gives us a great deal more flexibility when investigating the difference in the sample means. So there's two major differences in this test and the previous tests, and here we just assume that the population standard deviations, although unknown, are equal. So because of this assumption, we pool the sample standard deviations and we use a test statistic, the t-statistic. All right, so how do we find the t-statistic for the pooled t-test? Well, the first thing we need to calculate is the pooled variance, and the pooled variance, SP squared, S squared variance, P pooled, is we take the sample size of each group, so n1 minus 1, times the variance of sample 1, plus n2 minus 1 times the variance of sample 2, divided by n1 plus n2 minus 2. This denominator here, n1 plus n2 minus 2, this is in fact the degrees of freedom for this problem. So when you look at your t-table, this is the degrees of freedom you're going to be using, n1 plus n2 minus 2 for the pooled t-test. Now the t-test statistic, right, this is effectively step 5 of the problem, right? This is the t is x1 minus x2 divided by the square root of the pooled variance times 1 over the sample size of 1 plus 1 over the sample size of 2. The next series of slides will go through an example of this process. Right, so first question, comparing population means, equal unknown population variances. So the pooled t-test, again, we're making a few assumptions about the general format of these standard deviations, but we're going to assume that the population standard deviations are equal. So our question is there a difference in the mean mounting times between the two different techniques? We're going to use a 10% level of significance. The next slide will go through a full solution of the pooled t-test and this problem in lots of detail. The pooled t-test, sample 1. Okay, so let's start with our data set here, or in our information. So our question here is there a difference in the mean time to mount an engine on the frames of the lawnmowers? We have two techniques that we're observing, the Wells method and the Atkins method. So this company wants to know if there's a better way to mount the engines, or it doesn't really not matter which way you mount them, the time is not any difference. So we're going to be testing this at the 10% level. Let's start off by setting up our hypothesis. So step 1, the null and alternate. So remember, the question here is based on the alternate hypothesis. So is there a difference means that if we set this up, we'll say the mean Wells is no different than mean Atkins, which means the null will be the mean Wells is equal to the mean of Atkins. Since we're not given a direction, this is going to be a two-tailed test. Okay, so let's go on to step 2. Step 2 is this is an alpha of 0.1 or 0.10. Step 3, this is going to be a t-test. Well, why is it a t-test? Because first of all, you don't know the population standard deviation, so sigma 1 and sigma 2 are unknown. We're going to make an assumption in this question that they are equal. There's not a way to know this by just looking at the data set itself. You have to conduct what's called an F-test, where you basically find the F statistic by taking the standard deviation or the variance of 1 versus the variance of 2 in order to calculate the F statistic and then compare it to a critical value. But we were not going to be doing this in this class. So you will be told if the standard deviations are equal or unequal. All right, so let's go on to step 4. So step 4 is our decision rule. Okay, so the decision rule is set up effectively the same way as it always was. This is going to be a t-test, so we're going to have a t critical value based on the degrees of freedom, alpha, and the number of tails. For the pooled t-test, the degrees of freedom are found by taking n1 plus n2 minus 2. There's a document that I uploaded called the 5 2-sample t-tests, the 5 2-sample tests, and in it you'll see division of all the different types of tests and the type of degrees of freedom that they have. So in this case, we had n1 was equal to 5, n2 was equal to 6, so the degrees of freedom for this problem are 5 plus 6 minus 2, or 9 degrees of freedom. As we already established, alpha is equal to 0.1, and this is a two-tailed test. Therefore, our t critical value in this case is going to be 1.833. Okay, so let's draw our diagram. Here's our t diagram. So we have negative 1.833 and positive 1.833. Okay, so here's our rejection regions. Okay, so if we get a test statistic between negative 1.83 and positive 1.83, we fail to reject. And when we fail to reject, in this case, we're basically saying that the two methods are not different from each other, they're the same. If we reject, we're saying that the methods are different from each other. Okay, so we have our region set up. Now we go on to step 5. Step 5 is the t-test, but before we can do that for the pooled variance, we need to set up the pooled variance test, and in fact what we need to find is the mean and standard deviation of each of our methods. So if we look at our data set here, if we enter that into our calculator, what we find is that the mean x bar for Wells is equal to 4 and x bar for Atkins is equal to 5. Right? When we calculate the standard deviation using the standard deviation equation, we get that the standard deviation for Wells is 2.9155 and the standard deviation for Atkins is 2.0976. Okay, now we need to calculate the pooled variance. So let's fill this in here into where we were working. So we have x bar Wells is 4, x bar Atkins is 5, S for Wells is 2.9155, and S for Atkins is 2.0976. Now we need our pooled variance, and the pooled variance is, remember, it's n Wells minus 1 times the variance of Wells squared, so the standard deviation of Wells squared, plus n Atkins minus 1 times the standard deviation of Atkins squared, which is basically the variance. And the denominator is n1 plus n2 minus 2. So the SP squared in this case will be 5 minus 1 times 2.9155 squared plus 6 minus 1, 2.0976 squared, all divided by 5 plus 6 plus minus 2. And the pooled variance is 6.222. Okay, so let's put that into the test statistic equation. So T equals X Wells minus X Atkins, X bar Wells minus X bar Atkins. And that's going to be 4 minus 5 divided by the square root of 6.222, 1 over 5 plus 1 over 6, and that gives us a value of negative 0.662. So now if we go to our diagram up top, our rejection regions, right, negative 0.62 is in the fail to reject region. So we fail to reject the null, and we conclude that there really is no difference, or there is not enough evidence. So not enough evidence that Wells and Atkins have different times for assembly. So the first question, the alternate hypothesis question here, is there a difference in the mean mounting times? We would say no, there is not a difference. Okay. Now don't forget, we do have a step 6, right? And don't forget, step 6 is our p-value. So we need to find the p-value for this question. It'll be a fairly large number. We're going to fail to reject the null. But remember, degrees of freedom is 9. Okay, and we're going to be looking at 9 degrees of freedom on our t-table. Okay, and we're going to be looking at where would we find 0.66 in that table. Okay. Okay, so if you look at your table, what you'll notice, if we're really looking at the two-tail section, you have 0.2, you have 0.1, you have 0.05, right? And you'll notice that, and when you go to 9 degrees of freedom, the first number there is 1.383. The second number is 1.833, etc. Now, what you'll notice is that this 0.66 is going to come somewhere before this 1.33. Therefore, what you find is that the p-value is going to be greater than 0.2. And if we compare that to our level of alpha, right, which was 0.1, the p is greater than alpha, and therefore we fail to reject the null. Or there's not enough evidence to reject the null and conclude that there's a difference in the mean assembly times. All right, the second type of t. Okay, so as we saw in this question, the decision is not to reject the null hypothesis because 0.662 falls within the region between negative 1.833 and positive 1.833. So therefore, there is not enough evidence that there is a difference in the mean times to mount the engine. All right, comparing population means with unknown and unequal population standard deviation. So this is the second type of t-test. So here, the difference between this test and the one we just did with the pooled test is, well, first off, the formula, which goes into step 5. The formula, notice that it's not a pooled variance in the denominator, whereas the standard deviations are separated. And the other really big important feature is that the degrees of freedom has a fairly complex formula. This formula is meant to actually adjust degrees of freedom downward. It's almost like a like an average between the two degrees of, between the two sample sizes, but this is the formulation you would use when you're doing this type of process. All right, let's look at our first sample question. So here we're looking at comparing paper towel absorbencies. So the store wishes to compare a set of store brand towels versus name brand towels. So they've selected a random sample of 9 store brand towels represented here and 12 name brand towels. And our hypothesis question, our alternate hypothesis question is, using the 10% level, is there a difference in the mean amount of liquid absorbed by the two types of paper towels? All right, so the next slide we'll go through a tutorial video of solving this full problem. Unknown but unequal standard deviations. All right, so let's look at this question. So this question is asking to basically figure out what is the paper towel absorbency. So here we have a series of store brand paper towels. Okay, so this is store brand and this is name brand. So think of this as like Vaughn's brand or Ralph's brand, and this is like Bounty. Okay, and so our question in this case is basically, using the 10% level, is there a difference in the mean amount of liquid absorbed by the two types of paper towel? So we want to know, is there really a difference between store brand paper towel versus name brand paper towel? Okay, so let's start setting this up. The real big difference that we're going to see from the pooled t-test, going from the pooled to the unequal t-test, is that you're going to have a different degrees of freedom equation and you're not going to need a pooled variance in this case. But let's set up the equation. Let's set up the problem. So number one, step one, null alternate. Okay, so the alternate hypothesis in this case is basically to say there is a difference. So you'd say the mu of the store brand is not equal to the mu of the name brand. Okay, so the null would be mu s is equal to mu n. Okay, so again, since there's no direction, we're not saying one is better than the other or more absorbent than the other. So this is going to be a two-tailed test. Step 2, alpha is going to be 0.1. And I know the last two problems we had an alpha of 0.1, but really it could be anything that's on the t-table. Step 3, this is going to be a t-test. And specifically, it's going to be an unequal variance or unequal standard deviation t-test because sigma 1 and sigma 2 are unknown. Okay, so we're going to have to solve for the sample standard deviations. Okay, step 4, the decision rule. All right, so in this case, there is a little bit of difficulty, and that is in the equation for the degrees of freedom. Okay, I'm going to write this out for you guys as it's a little bit tricky. Hopefully I get it right. Okay, so let's start with the numerator. We have the variance of 1 divided by n1 plus the variance of 2 divided by n2. Okay, and then this whole thing is squared. Okay, now the denominator. The denominator, we have s1 squared over n1. Okay, that's squared. Plus, divided by n1 minus 1 plus s2 squared over n2. This is also squared, and this gets divided by n2 minus 1. Okay, so in this case, what we need before we really move on and even solve this part is to get the means and standard deviations for this problem. Okay, so let's solve for those. Okay, so we'll just solve these here on the bottom. You have the data. I recommend you pause this video and solve them yourself and check your work. So let's start with the mean, X bar for the store brand is going to be, of course, the sum of all the store brand divided by the number of observations, which is 9. So in this case, we get a mean of 6.44, and we get a standard deviation for our store brand ones as 3.32. Our name brand paper towels are a mean of 9.417 and a standard deviation of 1.621. Okay. Now our degrees of freedom in this case, once we plug in all those fun values, so let me see if we can do this fairly quickly. So we get 3.321 divided by 9. Okay, so that's squared, plus 1.621 squared divided by 12. Then remember, this whole thing gets squared. The denominator is going to be 3.32 over 9. And all that is squared. This gets divided by 9 minus 1. Plus 1.621 squared over 12, then that whole thing gets squared, and we divide that by 12 minus 1. Now if you go through the whole process and the order of operations correctly, you should get 10.86. Now what you're going to do with this is you're actually going to round it down. So no matter what the degrees of freedom is, no matter what the decimal is, you always round down. So in this case, we're going to use a degrees of freedom of 10. What this equation actually does is it takes these two values, the n1 and n2, and it actually shrinks them to the lowest possible degrees of freedom. And that's why we round down. Okay, so now we have a degrees of freedom of 10. So to find our t critical value, remember it depends on degrees of freedom, alpha, and the number of tails. Degrees of freedom is 10. Alpha is 0.1, and we have 2 tails. So our t critical value in this case is going to be negative 1.812. Okay, so let's draw the distribution. Okay, so since it's two-sided, we have negative 1.812, positive 1.812, and here's our rejection region. So again, if we get a value greater than our critical values, we reject, less than, we reject, and of course in the middle, we fail to reject. Now we can finally go on to step 5. Okay, and step 5 is going to be just purely our t-test. So t is equal to x1 minus x2, so it's 6.444 minus 9.417. You divide that by the square root of the variance of 1, 3.321 squared, divided by 9, plus the variance of 2 over 12, and this gives us a value of negative 2.474. All right, so if we go to our distribution here, our critical values, negative 2.474 is clearly in our rejection region, so we reject the null. So what do we conclude? We conclude, in fact, that there is a difference between the name brand and store brand paper towels, and therefore we accept the alternate hypothesis that the mean of the store brand is not the same as the name brand. Okay, so we reject the null. So if we go to this question that started this series, we said, is there a difference in the mean amount of liquid absorbed by the two types of paper towels? The answer would be an absolute yes. Now we need the p-value. Okay, so step 6, our p-value. So p-value, remember our degrees of freedom is 10. Okay, so if we look at our table and we look for 2.474, again, so if we had our t statistics, here's degrees of freedom, it's degrees of freedom of 10. Again, our two tail values, so 0.2, 0.1, 0.05, 0.02, etc. If we look at this chart, we find that 2.474 is somewhere between 0.05 and 0.02, so somewhere right in between those two here. So it's between the values of 2.228, which is this one, and 2.764. Okay, so what we would say is that the p-value is between 0.02 and 0.05, which are clearly smaller than our alpha of 10%. So once again, we reject the null, and we can conclude that name brand paper towels and store brand paper towels absorption rates are not the same. Okay, the two sample tests of dependent samples. So what we see here is we get a new test statistic in this case, and we find that the test statistic is found by taking the D bar, and D bar is the mean difference, and you divide it by the standard deviation of the difference between the two either time periods or the two prices, etc., and dividing it by the square root of n. This looks very similar to our Z equation from chapter 7. The other difference in this section is that the degrees of freedom for a dependent sample is n minus 1. Okay, so the degrees of freedom is n minus 1. All right, so this is the next slide will set up a problem. So we have this question. It says Nichols Savings and Loan wishes to compare two companies it uses to appraise the value of residential homes. Nichols Savings selected a sample of 10 residential properties and scheduled both for an appraisal. The results are reported in thousands, which doesn't matter in this case. And we're going to test the following. At the 5% level, can we conclude there is a difference in the mean appraisal value of the homes? The next slide, we'll go through a tutorial and solve this question in its entirety. So this is when we're testing dependent samples. Remember, dependent samples mean we're testing the same object or subject across time or by different entities, etc. So for example, if you started a new diet and you were interested to know if it was effective, you would be weighed at the beginning of the diet and then at the end, and therefore you'd be the same subject being weighed at different time periods, and that's when you would use a dependent t-test. Okay, so let's look at this question. It says Nichols Savings and Loan wishes to compare two companies it uses to appraise the value of residential home. Nichols Savings selected 10 residential properties and scheduled both firms for an appraisal. The results are reported in thousands of dollars. We don't really have to worry about that. And our question, at the 5% level, can we conclude that there is a difference in the mean appraised value of the homes? So there is our hypothesis, our alternate hypothesis. All right, so I'm going to set up the entire problem and then we'll see where we make our modifications. Again, the modifications are going to be in the degrees of freedom and in our last step where we calculate our test statistic. Okay, so let's start with our null and alternate hypothesis. So H1 is that their mu Shadic is not equal to mu Boyer. Mu Shadic is equal to mu Boyer. Again, since there's no direction implied in this case, we're going to say that this is a two-tailed test. There's also an alternative way to show the hypothesis test for this type of problem, which I don't really want to necessarily go through as it makes things a little bit more weird and confusing, but I'm going to write them down just in case. The alternate way of showing the null and alternate for dependent test looks like this. If you're looking for if there's a difference, you set up the alternate as difference is not equal to 0, implying there's a difference. And the null would be that the difference is equal to 0, stating that there is no difference between the two groups. So that's the alternate way of writing the null and alternate for dependent samples. Step 2, alpha is 0.05, given in the problem. Step 3, as we're basically looking at the same object by two different entities, this is going to be a dependent t-test. Anytime you see the words before and after, or you're looking at, again, the same subject over time or object over time, it's your dependent t-test. Okay, step 4 is our decision rule. Now, as we saw, the degrees of freedom vary from group to group. So in this case, the degrees of freedom for a dependent sample are simply n minus 1. Because you only, in this case, for example, you're only looking at these 10 homes, right? That's your entire sample. And so the degrees of freedom are just n minus 1 because that's the number of observations that are free to vary when calculating the mean. So in this case, we have 10 minus 1, or 9 degrees of freedom. Right? So to get our t-values, again, it's a two-tailed test. We have t critical value based on 9 degrees of freedom, alpha of 0.05, and a two-tailed test. That gives us a t-statistic of 2.262. So negative 2.262, positive 2.262. And here's our rejection regions. So reject and reject. And of course the middle area is our fail to reject region. All right, so step 5 is a little bit different now. So for step 5, we need to do a little bit of work. We need to calculate a statistic as you saw in that distribution. Okay, so remember the t statistic is d bar over sd divided by the square root of n. D bar is the mean difference between the two groups. So in this case, the difference in appraisal value between S and B, right? That's going to be D bar. This is the standard deviation of the differences between the two groups. Okay, so what we need to do first is we need to calculate the mean and the standard deviation before we can plug them into that equation. Okay, so let's have a look at our information here. All right, so here we have our data, right? We have, for example, we have Shadix and Boyer. So in order to calculate our difference equation, we're going to basically calculate a difference between the two. So difference is S minus B, we'll call it. So the first one will be 235 minus 228. That difference is going to be 7. The second is 5. 231 minus 219, that's 12. 2. Then we have 7, 7, 4, negative 5, 3, and 4. Okay, so there's our differences. Now remember, to get the standard, to get the mean, we have to add up all the differences and divide by n. So we add up this column and we get 46. We divide that by the 10 observations and find that the mean difference is 4.6. Now for the standard deviation, just like we calculated standard deviation before, we just do d minus d bar squared. The difference is squared. And we have 5.76, 0.16, 54.76, 6.76, 5.76, 0.36, 92.16, 2.56, and 0.36. So the sum of this column is 174.4. But remember, to get the standard deviation, we do the square root of 174.4 divided by n minus 1, 10 minus 1. So the standard deviation is 4.402. So we have our mean and our standard deviation. So now we can plug it into our t equation. So t is equal to 4.6 divided by 4.402 over the square root of 10, and this gives us a t statistic of 3.305. Right, so when we look at our critical values here, 3.305 is out there in this tail, and therefore we reject the null. And we find that there is a difference in the appraisal values of the homes by the companies. So S is not equal to B. Okay, so that's our finding. Just to go back to the question and answer it, At the 5% level, can we conclude there is a difference in the mean appraised value of the homes? The answer would be, in fact, yes. And for our p-value, so step 6, for our p-value, we would have 9 degrees of freedom. 3.3 is somewhere between 0.005 and 0.01 and 0.0001. Okay, so the p-value is going to be between 0.01 and 0.001. Very small. And we know that p is smaller than alpha, therefore we further reject the null. Okay, so that concludes our 3 different types of t-tests. Okay, so in this case, we found that there is a difference between the mean of appraised homes by each of the different companies. One last component here is when we're thinking about dependent versus independent samples, how do we know? Well, the dependent sample is characterized by a measurement followed by an intervention of some kind and then another measurement. This could be a before and after. Dependent sample is characterized by matching or pairing observations. So why do we prefer dependent samples to independent samples? Well, by using dependent samples, we are able to reduce the variation in the sampling distribution. All right, well, that concludes chapter 11. Please make sure you do the practice problems and the connect problems. Of course, we will do another set of practice problems during our next Zoom session.